All right, I hope that we are on. Good, and let's start again with the announcement. So as you see that quiz 30 to 32 are due end of week 14. And then PA8 is doing also today. Hi, Jingxiang. All right, good to see you guys popping up. All right. And so these will be the topics for the first hour. We'll start by talking about hierarchical addressing, which we started last week, but we have not yet started talking about the interesting part. And by the way, the interesting part, in order to start that, let me go back and review a little bit. What is hierarchical addressing? You see, right, earlier, our admin could acquire a block of IP addresses from the higher being, for example, from our admin's ISP. So we see an example like this, right, with prefix 20 bits long. This ISP can further allocate these IP address space to A equal parts, A organizations underneath ISP in a very easy way. Just use the next 3 bits to separate the A organizations. But as a result, the IP address space can be used by each of the organization gets lower. So you see that the benefit of assigning IP addresses this way, and you see that there's a hierarchy there, right? So higher being having a bigger block of IP address, and then after they are passed down and on, right? A organizations, and I think earlier we had an example in the video. Organization 7 can be further broken into 4 parts, right? 4 subdivisions, and each get a quarter of organization 7's IP address. So being hierarchical in addressing the internet machines, so you see a benefit. It's easy to pass the IP addresses down. There's another benefit, which is this, okay? Doing very efficient advertisements to enable routing. So this is advertisements of routing information so that the routers can do the best route computation. Okay. So with hierarchical addressing, these advertisements can also be sent in an efficient way. But in order to make sure that you understand, you see the benefit, okay, I have to explain a little bit how internet routing, okay, at a very high level between the domains, between the ISPs, between the ISPs to the internet backbone, how it works. And that is the first video. The goal of routing is to form these forwarding tables, if you recall, right? Destination IP and outgoing interface. Now, the way these entries are formed is this. If this is a destination, if somebody else on the internet wants to send data to this guy will need to announce its IP address, okay, in an advertisement and travel through the network like this to outside. Okay? That is how the router here discovered, oh, okay, I see a destination potentially this way. So that IP here, and yeah, the outgoing interface is this guy here. Now for a guy, okay, who's connected to the internet this way, that advertisement will go down, yeah, this other interface. So this other guy here, IP prime, yeah, the output interface will be linked here. Yes, that is the general idea of routing. But then you see, for each machine here having an IP address, in order to allow other people sending packets to it, they would each need to send an advertisement announcing its IP address. Okay? And there are these many different IP addresses possible, so potentially worst case, right? Lots of advertisements each of these organizations need to send and travel on these links. And you know what? The most scary thing is this. All these need to go out to the internet, so the ISP needs to send these many advertisements. And that is just not going to scale. Okay, there will be a lot of bandwidth consumption just to send the advertisements. The solution is actually related to the forwarding mechanism in the router. If you recall, instead of listing individual destination IP here, rather we do this, individual prefix, okay, and then outgoing interface. So when a packet arrives, the destination IP address matching the prefix, then we send it out on the outgoing interface. You know what? Isn't this a prefix? Isn't this a prefix? So, what we're doing, in fact, in the internet is not to send individual IP address in the advertisement. We send an individual prefix in the advertisement. So, what's happening there is a prefix in the advertisement gets here. Router here, receiving it, pass it down further. Router here, receiving it, pass it down further, but also add the entry prefix here. And because it's coming this way, so this OIF is going to point to this interface. So when a packet arrives here, matching the prefix, go on this interface, and coming here, this router is going to forward it similarly down this way. And then coming into the organization 0. So by announcing or advertising the prefix, okay, we also draw the data into the organization. And the data is actually destined for one of the hosts in the subnet anyway. So the routers inside the subnet there, we just, we'll be doing further routing there to get to the final destination. Nice. So you see, instead, organization 0, 1, 2, all the way to 7 will be sending one advertisements only instead of these many advertisements. What's even nicer is this, the ISP. Yeah, ISP doesn't need to send 8 individual advertisements out, just send one. Because it's very easy to aggregate all these, right? Because this is the coarser granularity covering, right? Superset of all these subnets prefix. So there's just one advertisement out this way. One on the link, one on this link, one on this link. Advertisements, the distribution of it, very, very efficient. And so here, the entry is simply 200 something something 6.0, and it goes on this interface. Data matching this will all fit and then go on here. This router here that will split the packet 8 ways, and by checking the destination address of the packet to these 8 different prefixes and see which prefix match better. So that is the idea, and why we say more bandwidth here. This is the third benefit of doing the prefix matching, in addition to what? Making the forwarding table smaller and the lookup process faster. Alright, so that was internet routing roughly, and you see the benefit of doing hierarchical addressing because you allow aggregation also in the route advertisements. Next is a short video talking about a really odd case that James was curious about. I think at some point Yilde also had the same question, right? We see earlier in the routing table we could have prefixes that have IP address overlap. How can that be happening, right? Yeah, this is the case, you see why. So the slide here is actually introducing a very interesting scenario. Okay. Organization 1 originally here is moved down here to a different ISP. So that prefix advertisement will travel down this way, and ISPRS will try to aggregate it with the original IP address block. Well, ISPRS will find that unfortunately the two of them are not aggregatable. In this case, 2 separate advertisements will go on out into the internet. The forwarding table here will contain 2 entries. One is starting with 199 and one starts 200 dot something 18.0 and 23 bits. This one is 16 bits. And of course, this entry here, will arrive also at the router here at the internet, on the internet. And therefore you have 200 dot something, 16 and 20 here. So this entry is going to take the packet out this interface. These two entries is going to take packet out here. So if there is a packet coming in that is supposed to go to organization 0, it's going to match the first entry, isn't it? It's not going to match the, entry number 3 because, hey, this address space and this address space, they are actually disjoint. Okay? So not going to match this guy here. So packet going for destination organization 0 is going to go down and travel and down to organization 0. So setting up the forwarding table this way, not a problem. Similarly for organization 2 and 3 and all the way to 7. Okay? As long as the destination IP address is matching this, it's going to come down this way. Yeah, I know you're thinking, hey, what if the packet is going for organization 1? You're right, it's going to match the first entry. Ooh, a bit worrisome, yes. But if you look down the table, right, hey, it's going to also match entry number 3. Now, if we recall back in section 4.2, what did we say? We're actually not just doing prefix matching. We are doing what? Longest prefix match. So which one is the longer prefix? 20 versus 23. So packet carrying destination for organization 1's machine is going to come down this way here and eventually reaching organization 1. So we're okay, right? So the overhead of sending the advertisements is still very low. Now slightly higher here if it's not exactly aggregatable, but forwarding is going to be fine. And we allow what? Organizations moving from one ISP to another ISP without changing the physical IP addresses. Okay? Therefore, all these servers are running here. They can stay using the same IP address without needing to change the name to IP address mapping. Now, we get the block of IP addresses from our ISP, but next question to ask. How does the ISP get its own block of IP addresses? So it's like saying, hey, the system admin asks the higher level system admin, but higher level system admin asks the even higher level system admin, right? And this goes on. Who's the highest level system admin? Where's the end? Yeah, this organization is the end. So ICANN here is the highest level system admin. This is a non-profit organization overlooking, okay, the allocation of the IP addresses, the allocations of the domain names, and managing also the domain name servers. So very important organization. We normally don't know. Okay, only the people who knows about the internet knows a little bit about ICANN. All right, so that was hierarchical addressing. Interesting, isn't it? Next topic in chapter 4.3 is NAT and AT. This is also something a little bit like DHCP that we use almost every day. And there'll be 3 short videos, each about 4 or 5 minutes. And we'll start by talking about the benefits of having NAT, the Network Address Translation Service. This is one of the most used protocol on the internet these days. It's here to address a very serious problem. We're running out of IP address space. Yeah, 2 to the power of 32, it sounds like a high number, but we do have a lot more hosts, a lot more router with network interfaces requiring these IP addresses. Therefore, IP addresses is a scarce resource on the internet. To get one, you pay quite a bit of money. This is also why, okay, if this is home network here behind the local network, your deal with the ISP is often this. You pay a specific amount of money monthly. You get a certain downlink bandwidth, certain uplink bandwidth, and a certain number of IP addresses. Usually you get 1 static IP address or 4 dynamic ones. Okay? If you pay more, maybe 8 dynamic ones. But essentially, the more IP addresses you need being allocated from the ISP, the more money you pay. So it's not like every family can afford paying that much. So to try to save money, this is what we often do at home. Okay? We just, subscribe for one IP address. And then we create a home network, okay, using some fake IP addresses that we make up, and subnet address that we make up. So instead of asking the ISP, okay, asking the system admin for a block of IP addresses, we can afford it. We use fake, okay, block of IP addresses. So we call this local network or home network. Each of the interface is assigned an IP address on the fake subnet. Okay, so these are then fake IP addresses. Now, as long as we are sending data within ourselves, should be fine. But if we want to send data out, wow, we need to be careful. And that's when we need a NAT server here at the home gateway. So NAT is sitting right here. So all packets that's leaving the local network needs to be using the real IP address, the IP address assigned by the ISP. Otherwise, it's going to be dropped, okay, at the ISP. So now, if this guy has a connection to go out, and this guy has a connection to go out, and this guy has a connection to go out, yeah, each of these connections to not collide to each other will be assigned a new port number as well here, okay, a different source port number. Source IP address changed to the global IP, the real IP, and the port number changed to a different number so that they don't collide to each other. So that is the general idea of NAT. We'll describe the detailed mechanism slightly later. What's nice about NAT is this. We don't need to ask the ISP for a block of IP addresses, which is very expensive. One is enough, save us lots of money. There are 3 more benefits, in fact, using NAT. One is this. If we want to change the IP address in the local network, we just change it. It's not like, we're changing the IP addresses of the gateway there, which is a global ISP, which is assigned by the ISP. Then we need to inform the ISP we're changing it to somewhere else. Otherwise, traffic is not going to flow through. Okay? But if we're just changing the local machine, then there's no need of informing the ISP. Nice, convenient, so save us time. Third benefit. Well, if the ISP is not providing good enough service, we can actually switch to different ISP. And the IP addresses we have on the local machines, we don't have to reconfigure them. We just stay using the same fake subnet address, fake IP addresses. The last benefit is slightly unexpected to many of you. Okay. Those devices inside the local network, those 10.0.0.1, 10.0.0.2, those IP addresses are fake ones. Packets originated from outside, from the internet, carrying destination 10.0.0.1 is not going to flow through the internet and reaching the gateway and therefore coming back to the host. Because the IP address of the gateway is what? 138.something. That's the real IP address. That is also what people call the global IP address. And that fake address there is the virtual address, the subnet address. Okay. So subnet or virtual address or fake IP addresses are not addressable. By not addressable is, what I meant is packets coming originated from outside just have no way of reaching. So they are therefore not visible from the internet, not visible from hackers in the internet. So it's a security plus, unexpectedly. All right, so that's the benefit of NAT. Let's take a closer look at the mechanism. NAT's mechanism is quite straightforward. Only 3 steps, 1, 2, and 3. Step number 1, you heard about it a bit already. So this is to handle when packet is going out from the local net to the world. We'll have to replace the fake IP address with the real one. We'll also replace the source port number with a new port number. Okay, so the source IP address, the source port number, these 2 fields are replaced with these two values. And this pair, so 1, 2, 3, 4, okay, are also tracked, okay, being remembered in Net's translation table. So the source IP and the source port number, as well as the translated source IP, source port number, will be maintained as a pair in the translation table. So when the remote host receiving this packet and sends back a response, in the destination IP address, it's going to be the real IP address, and it's going to be the new port number. So that packet coming into the local net, the net box there is going to look up the table and find the pair, right? So it's matching this IP address and matching this new port number, and therefore translate the IP address back to the corresponding port IP, source IP address, and translate the port number to the corresponding original source port number. And therefore, you see the destination fields is going to be replaced by the original IP and the original port number. And that packet then will travel the local network and reaching the destination. Let's use some animation to illustrate. It will be easier to understand. So the local net here, using a fake subnet address. So this machine here, 10.0.0.1, is sending a packet to a web server, okay, outside of the local network, okay, inside the internet. The packet is going to look like this. Source IP being the fake IP. Source port number being the port the web browser is sitting on. Destination IP, the server's IP. Port number, the web server's port number. So that packet is going to reach the net box in the middle, and this is going to be replaced. This is going to be replaced. So 10.0.0.1 is going to be replaced by the real IP. And the 3345 port number is going to be replaced by a new port number generated by the net box here. Step 2, the net router there is going to add an entry into the translation table so that we know this old IP, this old port number is now being changed to this new IP and this new port number. When this packet reaches the web server sends back a response. Destination address will be the source of the request. Okay. So destination port, the source port number of the request. Now this packet will come back to the net box in the middle, and one more translation is going to be done. So this time, the process exactly is this. Let's look at the destination port number, and then go to the table. Look up the entry in the table such that the port number in the WAN part matches the destination port number. Now, destination IP address is definitely going to match the WAN side of IP address, because the WAN side IP address is going to be just 138.76.29.7. So this unique new port number is the key. So destination port number, you look up this value in the translation table. Identify the entry, and then replace the destination IP address with the LAN side address. Okay, port number also with the LAN side port number. And that's why we see destination IP address, now the fake IP. Port number, now the original browser's port number. That's how net works. All right, that should be relatively easy. Now we use it every day. It's really convenient, but it's not without issues. So the next video is to talk about the issues. Last are the drawbacks of net. Point number 1, port number, pretty short, 16 bits only. That is also saying we could have only up to 60,000 simultaneous connections. If the local network there is for home use, this is plenty. But if the local network there is for enterprise use, if a company is there trying to save money and subscribing to only one real IP address, having lots of employees, lots of machines inside, chances high the packets going for one flow might be mistaken, okay, with the other flows. Point number 2. Yeah, NET is controversial. In the previous slides, you might see the authors of the textbook referring to these NET devices as NET routers. The routers are what? These devices in the core of the internet. Now, routers implement only 3 layers of protocol: physical, link layer, and network layer. So routers are also called the layer 3 protocols. Now, layer 3 protocol is supposedly only accessing layer 3 packet header. Layer 2 protocol accessing layer 2 packet header. NET, if you think about the mechanism again, it's what? Replacing the IP address fields in the packet header. It's also replacing port number, okay, the port number fields in the packet header. IP address, yeah, that is a field in the, yeah, I know, layer 3 packet header. We learned about the IP packet format already. But port number, if you recall, in chapter 3, the transport layer, port numbers are there to differentiate different processes running on the host. It's actually a layer 4 notion. It's in the transport layer header, in the layer 4 header. So NET as a router should not be doing that. So those who are against NET boxes to address the network shortage, IP address shortage problem, okay, argue that we should probably, improve IPv4 such that we have more bits for the IP address field. So IPv6 is the next generation. It's using 128 bits for the IP address, much longer. We'll talk about this later. Point number 3, NET box. Yeah, hosts sitting behind NET box cannot be reached from a machine from outside. So that was actually presented as a benefit, a security benefit earlier, right? Hackers cannot be sending packets to 10.0.0.1 because that packet is just not going to go anywhere. Okay, not even reaching the NET box in the middle, the IP address being 138 something something. Right? Only packets with the destination address 138 something something will be able to reach NET box. And NET box there, it will also not know, right, what port number, what local IP address to convert back to reach 10.0.0.1. So, yeah, it's actually hard to reach local hosts from outside. So if packets are originated from outside, that's not going to work. Packets originated from inside, however, works. Now we know, right? So from 10.0.0.1, need the box tracks the local IP address. Okay, keep it in a table. That packet gets translated using global IP, using real IP, goes out. Packet will come back to the router and the NET box. Look up the table and then translate back. So originated from inside, no problem. But data originated from outside, big problem. And this is a serious problem for these designers, P2P protocol designers. In P2P protocol, a lot of time we will try to establish connections between one user's host to another user's host. You and me being hosts, we are, chances high, sitting behind the NET box, sitting behind the NET router. So we'll have trouble calling directly to each other, setting connection directly to each other. If you recall in Skype's protocol design, making a call, the designer of Skype actually take extra step. Okay? Bob and Alice will need to call a relay peer, and the relay peer will exchange packets for each other. Okay, for these two peers, for Alice and Bob. So, application layer designer now need to worry, okay, in case layer 3 or layer 4 protocol is gonna break. Okay, unexpected might happen. So, One layer's protocol designer needs to worry about another layer's how it's designed, how it works. That's breaking the end-to-end argument. So by this here, okay, what I'm saying is this. The reference protocol stack there, okay, application, transport, network layer. So we say nice about building the network protocols and separate them by layers so that it's modular. Designer in one layer does not need to care about what's inside another layer. Exactly the same thing we are arguing here. Application layer protocol needs to worry about another layer's protocol, how it works. So that breaks the modularity there we have in the original reference stack. And that is what end-to-end argument is referring to. All right, so that was net. So let me address a couple questions and then we'll move on to the first quiz today. So the first question was, what is WAN and what is LAN? Yeah, so WAN was simply wide area network. So that means usually the bigger global internet. And LAN is local area network. For example, you sitting at home is within the home network, a local area network. And then another question. And by the way, the first question is from Jingyuan and second question is from Wei Yao. Would it be visible from the outside if we know the transformation of the NAT, of NAT? Yes, now you know the mechanism, right? There's a NAT table there and there's a pair of IP address and port number translation. So if we know which port number for the NAT's global IP address, we can send packet and therefore it will go to 10.0.0.1 certain port number. Yes, we just send a packet with that NAT router IP and that port number. It's going to be translated back. But the presumption is also that that mapping entry is set. Okay, so in a way, the local host there will need to do something to set up such an entry in the NAT box before you can start sending packets to that specific port number so that the NAT box can translate it back and forward the packets inside. Okay. This is one of the techniques also for NAT traversal. You heard me saying, in Skype, right? They use a relay peer, and that relay peer needs to have global IP address. Therefore, each of these peers behind NAT can set up connection to the relay peer. And then from there, we exchange packets. So that's another way of doing NAT traversal. Okay, so Wei Yao, the thing you are asking is another way of doing NAT traversal. Good. So I guess you guys are also picking up what I was saying. Very good. So the video seems to be working. So now let's move on to quiz 13. Okay. So ideal versus practical. Oh, okay. I see Pei is asking a question. So Pei, let's hold on to your question until we finish the quiz. All right. So quiz 30 is this. Ideal and versus practical. Okay, so are you an idealistic person or a practical person? Okay, so Q1 here, simply asking you, subjectively, would you rather pay for multiple IP addresses for the machines at home? Or would you just pay for one and use NAT? Okay, feel free to choose whichever you like and tell me the reason. Q2, would you prefer using NAT or IPv6? Now you heard a little bit about, right, when we were talking about the controversies of NAT. IPv6 is saying that, hey, let's not do NAT. And we do have this IP address shortage problem. So how about we expand the IP address space from 32 bits only to 128 bits? Okay. So personally, would you prefer doing it the NAT way or the IPv6 way? Pick whatever you like better, but justify. Tell me why. Okay, good. So now let's move to the Slack space and type up whatever you have there. Yeah, definitely find your teammate. I hope that you guys do not have conflicting choices. Well, if that's the case, feel free to type up the reasons for each of you. Feel free. Oh, wow. Okay, good. Okay, good. So Samuel, and Jean of Team 12 have reached consensus. Okay, so they would prefer using net because, oh, okay, poor you, you're poor, okay. And A2. We like IPv6 better because the rules should be followed. Oh, wow. Okay, absolutely cool. Okay, this is also, especially this is so during the COVID-19 season, that is particularly okay the right choice to make. Okay, let's follow the rules and stay home. Very well done. Oh, I see people. Several people are typing. Yeah, I guess. Oh, okay. Quite to all machines. Yeah, I think recent operating systems, if you update your Windows to the newer version or Mac OS to the newer version, so I'm not quite sure about iOS or Android, but the newer versions of the operating systems are all IPv6 capable. And the newer network interface cards or interface chips are all IPv6 capable. So what's really stopping us from moving to IPv6 are actually the routers between us and the core of the internet. Yeah, you guys are typing forever. Well, let's see. Oh, okay, good. Good to know. Very good to know. IPv6 is also in iOS. Well, in this case, then I think it's chances also high that it's in Android. 舒伟, Team 3. Okay, so you guys prefer NAT to save money, of course. And you guys prefer NAT also over IPv6. Okay, IPv6 address is too long to remember. Yeah, I know, to do the PA assignments. Oh, it will be a headache, isn't it? I think that's a valid point. I've gotta give you that. Yeah, the PA server's IP address. Try to remember that. Or try to type up that number. Okay, so Lin Boxin, okay, Team 4. Good. Both, just like Team 3, right? NAT and NAT. NAT to save money and NAT over IPv6. Okay, because, yeah, more memory space. Oh, very good point. Push companies to change from IPv4 to IPv6. Yeah. So in fact, none of us are resisting IPv6. The operating systems are already automatically looking. In case the first hop router that we are connected to is running IPv6, the host is going to generate IPv6 packets. Yeah, but as you said, Boxin, I think that's a very good point. But from a system perspective, right? Less philosophical, but or not economical, but system wise speaking, saving memory space. Oh, okay, good. All of a sudden. I don't know about you guys. I've recently discovered that there's a certain delay that I receive your Slack messages. So I'm guessing that Slack is also busy these days relaying messages. Alright, so let's see. Jia Hong here is saying, okay, NAT, reduce costs. So when it comes to money, I think nobody says no to money, isn't it? I would be very interested to see an answer for Q1 saying paying for multiple IP addresses and providing a reason for it. Okay. Jia Hong here prefer IPv6. We think that doing more transfer is not so convenient. I see. I think you have a very good point. I think you're going and having a net box there in the middle to do translation. That takes time as well. Very good. So I hope that my interpretation is right. Okay, let me know if I am correct. Interesting. Also, maybe in future IPv6 is applied by more machines. Indeed. Kevin here for Team 15. NAT, in order to save money, of course. Otherwise, I'll have to pay money for on my cell phone, pad, notebook. Yeah, for each of the devices, isn't it? Good. And I like IPv6 since even we use NAT, lack of IP addresses of IPv4 isn't evitable. It will be a problem in near future. Yeah. Right. Very good. Yeah, it's usually better to use IPv6. NAT is actually something in the middle, translating. That's actually slightly, it's not much, but it's a slight overhead. I think Kevin is saying that even if we use NAT, we might still be running out of IP addresses. Okay, that's a very Insightful observation. Right? Each household needs to have a net, right? And then there are so many servers around these days. James and Yoda, yeah, you prefer net? Oh, okay. The preference is because, the reason is because of being more secure. Very good, James. Well done. And you guys prefer IPv6? If there are some problems with net, then all LAN cannot work. Very good. Yoda, that's very insightful as well. Yeah, because if the translation table, for example, is somewhat corrupted, the messages won't be able to go out or come back. Good point. Jingyuan here is saying, on behalf of Team 2, NAT and IPv6. Because you are poor too, okay? You want to get addresses in IPv6 before it becomes full. Oh, interesting. Very interesting point. Yeah, so you want to secure an IPv6 IP address before we run out of the address space, even though it's 128 bits. You know what? Guys, Team 2 is perfectly right. Think about this thing called IoT, Internet of Things. Yeah, so thermometers will have an IP address. Your weight scale will have an IP address. Maybe my water bottle here might have an IP address. You thought that 128 bits is large enough space. With all these things now all need an IP address. We could run out of the space real quick. Very good, guys. Okay, Team 1, and this is from Hongxuan. We would prefer paying for multiple IP addresses. Okay, great. Extra points for this one, because in that we won't have to set up net table and bother others to check out our translation. Yeah, this is actually really nice because then you can run servers internally. And maybe drawing traffic, and you can begin sell ads. So if you have experience building up servers to provide services for other people, then you might prefer purchasing real IP addresses. We like IPv6 more because the demands of addresses are very high now. More IP addresses to avoid future problems. Yeah, I guess your answer might translate to maybe we need an IPv7 with a even larger IP address space. Very good, well done. Alright, really cool. Eating here, save money +1, very good. IPv6, there are many incoming outgoing datagrams. Yeah, there might be some delay during the translation and more memory consumption for that box in the middle. Team 6. Yeah, net, because you save money. IPv6. Yeah. CI here. You can, I would highly recommend that you become a network engineer. This is very network engineers thinking. So each of us developing code in each layer would really like to be able to develop freely with minimum assumption. Otherwise, we might see suddenly things don't work. Very well done. Oh, did I check? Team 9. I think I did. All right, very good. And then Team 7. Okay, this is Lin. Okay, I think Cai Chang Lin, right? We would rather choose NAT because we cannot guarantee the number of hosts in our home. Oh, okay. You see, having IoTs We don't know how much IP addresses we would buy. Very good. You could purchase multiple IP addresses at the beginning when you sign the lease, sign the contract with the ISP. But what if you have more devices now all need IP addresses? Yeah, for example, Polly comes to the house as a guest. Okay, I might need internet access, right? How do I get an IP address? So Net provides also flexibility. So not just saving money, but flexibility. So then it's probably more trade-off, right? Saving money, flexibility, but on the other hand, right, memory space and slight delay translating the packet's source destination IP port number. You would prefer NAT since IPv4 has already existed for quite some time. I think you meant okay, you would use NAT. And changing the protocol for the whole internet seems to be very difficult work. Yeah. Designing mechanisms that can handle IPv4 and IPv6 for all devices seems tedious. Well, hey, Team 7 or Changling, you probably read into the next sets of slides, or you have already watched the video. It is indeed very challenging to push the entire internet to IPv6. Yeah, so for Q2, it's actually not clear whether you stay using NAT on IPv4 or you move on quickly to IPv6. Because in IPv6, if your machine are natively IPv6, there will be also some other translation you need to do if the path from you to the destination. There are some IPv4 routers. All right. So it's a little bit hard to tell whether doing it over NAT versus IPv6, which one is really more efficient. Trying to be practical. And Ethan, Team 13, NAT because it's more secure. Okay, so James, you have someone who feel the same with you. And IPv6 has better efficiency and simpler configuration. It is indeed. Usually you just have the DHCP and then the ISP automatically assign you IPv6 IP addresses. And there's no translation in the middle. Okay, very good. And you know what? It's time to take a break. So we'll resume 10 minutes later. And move on to IPv6 that you guys know a little bit about. Okay, so let's resume at 2:23. Break. Okay, let's restart. The next topic is IPv6. But before we start, let me go over the questions on either YouTube channel, chat, or on Slack. So I think Pei had the question. Why do we need to store the IP address of the NAT router if we only need to use the port number? Yeah, that's a very good question. We don't. We don't. Yeah. So that IP address is just gonna be there. So that can save some memory space. And then Guang Zhao was asking, okay, so this is a good question. The due date of PA9, and in fact the due date of PA8, both of them are not exactly updated, although that I already mentioned PA8 is doing end of this week. Okay, so let me take you to the web page. So this is the schedule of the course, and we kind of try to push PA8's due date down a week to address the chaos last week. Okay, and so PA8 should be doing May 29th, 6 p.m. But I know that some of you have already completed PA8. Good for you. And therefore PA9 will need to be pushed back 1 week as well, to June 5th. Okay. And I hope that's clear. But however, I have to let you know the last exam, it's not exactly like the regular final because we had very narrow scope each exam. Okay, so the last one will be about 5 days apart. Okay, May 5 to May 10th, only 5 days apart to the final exam. Okay, good. There's also a question. Let me just quickly slide over on Slack. So Samuel was asking, do IPv4 and IPv6 work independently or simultaneously? Okay, so this is a very interesting question. They sometimes need to work collaboratively. Okay, you will know more as we move on to IPv6, especially the second part of IPv6 called tunneling. Okay, but as a short answer for now, some machines, okay, will need to have both IPv4 and IPv6 working simultaneously. Okay, and who are these machines? These are the machines, okay, typically routers. Routers connecting a subnet that is strictly IPv4 to a subnet that's strictly IPv6, because that router needs to have both protocol, otherwise the router will not be able to handle the other subnet. Okay, so those routers sitting in between IPv4, IPv6 clouds will need to run IPv4 and 6 simultaneously and somehow cooperatively between the two implementations. And there's actually a translation service there as well. Okay, so you're seeing tunneling. But some of the machines on the internet don't have to. Okay, for example, the hosts. I mean, if we have native IPv6 gateway routers, they're at home. We could just run IPv6. Most of the operating systems have both support on the clients, okay? But that doesn't mean that they're running simultaneously. It's only active one or the other. That's why you see in your network interface card, it's either that the IPv6 interfaces, it's either the interfaces in the IPv6 mode being active or the IPv4 mode being active. And then, there's a second part of the question. How do we know we're using IPv4 or IPv6? Okay, this is a very good question. I mean, the way I do it is I simply check my IP address, the machine's IP address. So there are ways to do the checking. So I'm using a Mac machine. So as you could see that the operating system of a Mac works like this. So if you go to the system preference or the startup menu and go to the setup, usually there's this option called network, and you see, okay, yeah. Speaking of using NAT, Poly is also using NAT, okay. For the exact reason that I have too many machines at home. And IP address you see here, is this IPv4 or 6? Obviously 6, right? Only 32 bits. Yeah, I'm using Google's DNS server here because it's a little bit more reliable than ISP provided DNS server. All right. If you're using Unix system, there's another way of checking it through command line. If config. So the output of the if config is to show all the interfaces you have on your machine, and if you go through these interfaces, so LO0 is the local looping interface. So this is the interface that address to the machine itself. Okay. EN0, I suppose this is the first network port I have there, and I should be. Oh, okay. So I'm not using it. Okay, I'm not using it. I'm using the other one, EN1. So my machine has two network interfaces. So, I do have the IPv6 MAC address. Is it? No, I do have the IPv6 IP addresses here. Okay. So my net box here actually supports IPv6. So I'm actually assigned through the DHCP on my net box an IPv6 address. But in the meantime, IPv4 address. Interesting. Well, by doing if config, it's actually less clear which IP address I'm using, which version of IP I'm using, because I do have both IPv4 and IPv6 IP addresses. Interesting. There's yet another IP address I'm using. So it's given another IP address. Another IPv6 address. All right. So this is just another way of checking if you're using Unix. If you're a Windows user, you can also start your system manual and then check there. Now let's resume. The next topic, IPv. Oh, okay. Curl, IP echo. Oh, there. Oh, okay. Yeah, so interesting. Yeah, I guess. Okay, so maybe we try. Yeah, I think it's a service out there allowing you to check whether you are really using IPv4 or 6. That's really nice to know. Yeah, so this must be my IP address for the netbox. Yeah. So yeah, internally IPv4 I'm using, and to close to outside, my ISP is also assigning IPv4. Yeah, it checks for the outside, definitely. Very good, thank you, Samuel. And now we move back to the next topic, IPv6. Now this video is a little bit long, but I will try to break in the middle somewhere. Take a pause in case you have questions. Last topic in 4.3, the IPv6. This is also the protocol some of these network engineers thought more legit, addressing the IP address shortage problem, instead of using these controversial netboxes. And that is why we actually upgrade from version 4 to version 6. approach is very straightforward, expanding the 32-bit IP address space to 128 bits long. So the main goal of having IPv6 is exactly this. There are two secondary goals. First is to speed up the processing or forwarding of the packets as they come into a router. So in the data plane, packets coming in really fast. If we could reduce the forwarding time, processing time, we made the transmission process as efficient as possible. So you'll see in IPv6, the header is also changed, okay, to try to reduce the forwarding time, the processing time. The secondary purpose, this. We want to add something so that we could label the packets, so we could separate a group of packets from other, okay, and make them flows, different flows. Now, with the different flows of these packets, we could then assign priority to a specific flow versus lower priority for other flows. Okay. Therefore, we could establish a more flexible levels of quality of service for these different flows. You see also header fields there to support labeling of flows, setting priority of the flows. The IPv6 packet format. The header part of it is fixed size and 40 bytes long. Now recall version 4. Is it fixed size or variable size? It's actually variable size because of the option fields there. So that field, in case we have more options, then it's going to go longer. No fields, 0. And therefore, IPv4 header size is 20 bytes minimum and could potentially be more. Now you probably recall, right? When we were talking about the IP header size, 20 bytes, we also mentioned the TCP header, 20 more bytes. Together, 40 bytes, just to store the control information. If we're sending a real message that's 10 bytes long, the entire packet will be this long, while only 10 of them is effectively sending data. This is very low utilization. So yeah, Poly kind of promised you that in the next version of IP, we're going to reduce the size of the header. But you see here, is 40 longer or 20? Yeah. 46 in fact has a longer header. But this is necessary, and this is as small, as short as possible already. Allow me to explain. In the IP packet header, there are two fields called the source IP and the destination IP. In version 4, the IP address space is only 4 bytes long. Now, to store source and destination IP, you only need 8 bytes. But in version 6, the main goal is to expand the IP address space. So unavoidably, we have very long IP address, and two of them, one for source IPs, another one for the destination IP, together 32 bytes. If you look at this, version 6 header 40 bytes, so we have only 8 bytes for the additional fields. While in version 4, 20 bytes long, we have 12 bytes for the additional fields. So the designer of IPv6, you see, try very hard to reduce these other unnecessary part of the header, removing them away, removing these fields away from the header. So 40 here, longer indeed, but it is actually after we try very hard making the header part as compact as possible, as small as possible. In fact, the second feature of the version 4 header is this. To recall in the fragmentation and reassembly function of IPv6, we have these 3 fields in a row. ID, fragmentation flag, and offset. This row of extra header fields remove entirely, okay, and this is done
by disabling the fragmentation and reassembly function in version 4. So in IPv6, no longer allowing fragmentation. And this is why we see the version 4 header, although longer, it looks really clean and compact.
Yeah, so that was the quick overview of IPv6, and you see a little bit of the shape of it. Now that's getting to the detail of each field.
First, the source address. Second, destination address. And the rest is only just 6 more. 1, 2, 3, 4, 5, 6. First, here is the payload length. If you recall in version 4, we do have what? The header length and the entire packet length. Because the header size can vary. And the packet size, because the data size can also be different, so we need 2 lengths. Here now, having a fixed packet header size, we need just the payload part, okay, the payload length to indicate the size of the data down here. Hop limit, this is just the TTL field, okay, just like in IPv4. Next header, it looks odd, we've never seen this before, but this is really the upper layer field in version 4. So what it does is, once we extract the payload, we actually forward the payload to what's indicated by this pointer here. And so further processing will be done using this handler on the payload. The version field. We also have this in version 4. So the only difference is that this value will always be 6 in version 6. Priority and flow label. These two are new. So flow label here is to allowing us to group a specific set of packets together. Okay, so coming from one application, coming from one service, they could be carrying flow ID 1, and other packets from other services, flow ID 2. So we could identify packets for one flow, okay, and packets for yet another flow. So we could separate these packets traveling the internet. As a result, we could then provide different priorities to different flows. So some flows will go earlier than the others. Therefore, we provide flexible levels of these QoS. Now, there are some more fields we remove, okay, not just the fragmentation fields. The header checksum in IPv4 header, that is removed because to calculate checksum takes time. To check the checksum takes also time. So let's try to reduce the forwarding processing time as much as we can. So let's remove the checksum part. And take the risk of some bits in the header being flipped. We might have some, we might run into some errors, but chance is very low. Okay. We way higher here, way more here, trying to make sure the forwarding part is fast. And we move the option part down to the payload so that when we grab the payload and give it to the handler is going to look at the first few lines in the payload, and those will contain the options. There's one more thing. ICMP version 6. What is ICMP? You need to think back. In one of the earlier overview slides, I was talking about the functions and protocols implemented in the network layer, right? In the data plane, we have forwarding. In the control plane, we have routing and management. ICMP is one of these protocols implementing the management function. So we also extend the version 4 ICMP to version 6. And the reason we need the version 6 ICMP is so that we could send a special message, packet too big. Allow me to elaborate. Now we don't have fragmentation and reassembly. But the fact that some of the links on the internet allows smaller MTU is still there. So what if we have big datagram coming to a router and the next link is saying MTU smaller? But we cannot fragment this datagram anymore. What should the router do? What can the router do? Okay, so the mechanism in version 6 is to send a special message, an ICMP version 6 message, back to the data source saying packet too big and the better packet size is below this MTU value. Okay, so there's additional message being defined in ICMP version 6, allowing the routers to manage themselves, deciding what is the best datagram size. And we'll just ignore this part. Multicast, we'll just not talk about it at all. Okay, it's a can of worms. So this is
all right. Yeah, that's IPv6. And we'll move to the second video of IPv6. Okay, so let me bring it up first. This is in fact the second part of the outline. So first is IPv6, it's called tunneling. So this is the technique we use to connect IPv4 and IPv6 clouds. And so
this topic is a little bit special, okay? We will be talking about how we move from a IPv4 internet to a IPv6 internet. You see, there's no way we turn down all the routers in the world and upgrade to version 6 simultaneously and turn them back on and hope that they will just work. No way. It's really, really risky. And hey, we are all, right, living in different time zones. What do you mean by having a flat day? And not to mention that turning the entire net down for an entire day, okay, and wait until all the debugging and upgrading is done. Well, yeah, some part of the world might panic. So how will the network operate with part of the internet running IPv4 and some other parts running IPv6? So transition from IPv4 to IPv6, this is what we meant to talk about. How do we allow the mix of IPv4 router to IPv6 routers? And the technique, okay, let me tell you ahead of time, is called tunneling. Okay, establishing tunnels, okay, between routers, okay, at the edge of the IPv6 network to IPv4 and then back to IPv6. And the technique is working this way. So if there's a packet generated from, the IPv6 space, so then the network layer in the machine in the IPv6 space will be generating an IPv6 packet. Okay. Once it hits, okay, this border between IPv6 and IPv4, this router standing at the border will be implementing both IPv4 and 6. So this router will also be doing this. Okay. Take the IPv4 packet generated from the take the IPv6 packet generated in the IPv6 space and encapsulate that into an IPv4 packet. Okay, so this is the IPv4 packet, okay, and this is the original IPv6 packet, okay, generated from the IPv6 space. So that IPv4 packet is encapsulated, so being contained, okay, in this bigger IPv4 packet. All right. So you see here, we'll have packet header fields here, source IP address, destination IP address, and etc., etc. Now, IPv4 packet here coming from the border of IPv4 and IPv6 connection is going to travel the IPv4 network fine because the header fields interpretable by the routers in the IPv4 space, and eventually reaching the other end, okay, the other border between IPv6 and IPv4. And that border router there would extract, okay, the IPv6 packet, the blue part here, from the IPv4 packet and then forward it further on onto the native IPv6 space here. Right? This enables an IPv6 machine talking to an IPv6 machine with the middle part being IPv4.
All right, so that's the general idea. We'll take a look at an animation. Okay.
I know, allow me to illustrate. So in the scenario, we have an IPv6 space to the left and another IPv6 space to the right. I suppose we have data we want to send from A to F. Okay? Both of them, version 6, they should be able to send data to each other all right. Now the problem is this. An IPv6 packet here will travel through the version 6 space. But as soon as it hits the version 4 space, these routers, they're old. They don't recognize the version 4 format. They will not be able to handle the packet and forward it down this way. Okay? And that is why we need tunnel. Okay. So what's being done, in the tunnel is this. B being the border router, E being the border router separating the version 4 and version 6 space. It's implementing version 6 for sure, but also version 4 as well. Therefore, B and E both carry IPv6 address as well as IPv4 address. By setting up tunnel, B now actually record E's version 4 IP address. E here records B's version 4 IP address. So essentially the two ends exchange the IPv4 address. So once that's done, usually this is done offline by the network admins. Once that is done, then let's consider A here generated the packet, the blue one, and we're forwarding it towards the destination. Right? Once it hits the border router here before the IPv4 space, B, the border router, is going to do this. Encapsulate the blue packet inside a version 4 packet. In the version 4 packet, the source address is going to be B itself. Destination address is going to be the other end of the tunnel. The other end of the tunnel's IPv4 address. Now, this is an IPv4 packet, source being B, destination being E, and the IPv4 network is capable of forwarding this packet over, at least to E. So E is going to receive the packet next, and being the border router, being the other end of the tunnel, E is just going to extract the blue packet out of the red one and forward it down to the rest of the IPv6 space. And this is when F here receives the packet that is supposed to go for F. Last slide here is not technical at all. It's to talk about the adoption of version 6. So Google once released this number. 8% of the clients worldwide accessing Google services are IPv6. Ouch, pretty low. NIST is a government body there tracking all sorts of standards as well as maintaining some statistics. So NIST releases this. 33% of the US government internet is IPv6. US government is promoting strongly the move to IPv6. And to make the numbers even more pathetic, this is after 20 years of effort. Ouch. But why, right? If you think at the application layer, we have new applications rising. IG, Facebook, Netflix, other video streamings, Zoom, YouTube, newer services rising. Within each service, the protocol also get upgraded quickly, right? Changing from one version to another version. But unlike application layer changes, Network layer changes. It seems very hard to do. It's not like undoable, right? We just need to upgrade the routers, upgrade the clients, reconfigure the routers, reconfigure the clients. Why is it so hard? Why is it so much easier to upgrade one app?
Why? That is quiz 31. Yeah, it seems really hard sometimes to make changes, all right? So the quiz here is, again, not that technical, but a little bit more philosophical. As you see that the trouble here we run into, okay, pushing internet forward is a little bit psychological, philosophical. Okay, so Q1 of quiz 31 is asking, have you ever thought about changing your way of life? I know this is a very big question. Think about it. Q2, if yes, did you end up making the change? Oh, by the way, first question is a yes or no question. Second is also a yes or no question. Okay, it's up to you. You don't have to really share what you want to change in case it's a little bit private. Q3, if you did make the change, was it easy or not? Now, if you choose to answer Q3, then you might need to tell a little bit more. What is the thing that you want to change? Okay, and so that you can explain, it's not that easy because of this or that. All right, so this is a very important question, guys. Okay, find your teammate. Okay, open your heart, talk to them, and share what you want to change, what you have ever thought about changing, and was it successful, yes or no, and why. Interesting. If I close and pop it up again, no. Oh, you guys are typing faster this time. Yeah, that's great. Oh boy. I knew you guys are gonna make me laugh. Great. Sue's life is great. Yeah, celebrate for Sue. Snaps. I mean, you know what? Life is generally nice, right? Isn't it? I can be lazy, staying home and not going anywhere. I thought I thought this is a geek stream lifestyle. So we should all thank COVID-19 so that we can just stay home. Oh, okay, let's see. IPv6 is for real. Nows? Owls? Surely. Mm-hmm. Yeah. For reals? Meows? Mm-hmm. Surely. Yeah, that way you don't have to answer Q2 and Q3. That's great. Hey, you guys, don't try to do the same thing. Alright? Okay, come on. Somebody opens up and share with us the things you want to you want to change for. It doesn't need to be you. It's something that you want other to change, maybe. Mm-hmm. Oh, wait, I see. Yeah, 谢维胜 here says yes. Ah, okay. Mm-hmm. Something that he wants change. And it worked a little bit. Mm-hmm. It wasn't easy at all. Making change means that you change your habit. It always takes me much time. This is very honest of you. Oh, it does, isn't it? Once you get used to something, it's just so hard. I know. So I'm guessing James will be probably saying the same thing, right? Yes, many times. Okay. Yes, I usually did. Very good. Very good. You do have a strong mind, James. I can see that in Yoda as well. You guys make a great team there. Not really easy. It took time. Yeah, so maybe Wei Sheng, I'm sorry. Maybe Wei Sheng, try it again. Then the change might be a little bit bigger. Yeah, it usually takes time. Yeah, like IPv6, right? 20 years and it's still not there. Sometimes I cannot see. And you know what? IPv6, everybody know that we need it. The fact is probably that we need IPv6 plus NAT, isn't it? And you just need to a bit anxious about we're still not in IPv6. Even that we all have NAT boxes already, still at some point we're gonna hit the limit. Not really easy. It took time. Sometimes I cannot see my own mistake after I met someone who caused me to reflect myself, and then I can finally know that I should make some change. Oh wow, okay. Yeah, I do also have a few hard lessons like you, James. Until I finally meet someone who's really honest and tell me what was wrong. It was not easy to take someone around me to say it. So appreciate people like that. If they are willing to tell you right in the face, this is wrong. I need to believe in myself more instead of caring too much about what others see me. Oh wow. Wonderful. 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 This might be generally true for many of you there. By the way, Polly really cares what others think of her. But when I'm teaching the class, I need to make sure that you guys love me. And so I do love you a lot. And I, for some reason, learned to play, learn to be an actress in a way. So that I cast myself into this shell that I'm a very caring, warm professor. So guys, be careful. I'm not really very loving and kind and caring. Okay. But you do know that teaching will be more effective if you feel the love. But still, hey, I love you guys, okay? And Johnny, on behalf of Team 4, yes, all the time, yeah, don't we? Not in any significant way. So, Johnny, the tone is a little bit disappointing, depressing. Yeah, I do notice you always sitting in the back. Oh, not excited of anything. Even though I feel that you're listening. Very interesting, your personality. The comfort zone is comfortable. The clue is in the name. Oh, is that a puzzle? Is that a riddle? Very interesting, Johnny. You are a very interesting spirit. Hey guys, let me know if you decrypt Johnny there. Okay, lots of love, Johnny. Double love. Okay, let me see if I can find another emoji that's also loving. Let's see. How about a piece of pizza? Yeah, you guys often like pizza. Or a pack of fries. There we go. Okay, let's see. Hongxuan on behalf of Team 1. Oh, that's a piglet note. I like that. Yes, no, life is hard. Ouch. Changing is even harder. So you are the opposite of, is that 正位 or 虚位? Yeah, opposite of 虚位. There. Okay. Samuel, oh, I neglected here. Yes, yes, yes. Okay. Yeah, that's a very simple answer there. Okay. Oh, you see, people feel for you. Okay, let me feel for you as well there. Life is hard. I guess for some of you, this is hard, right? Yeah, by the way, Polly has split personality. Very geeky in the meantime, very outdoory. I don't know. Johnny might also have that. A little bit of the split personality. So we are the odd kind. When I was younger, I thought I was from the outer space. I don't know if you feel sometimes that you're from an outer space, some other planet. Okay, there, some other planet. Team 19. Oh, Pei Yu. Yes, regular exercise and keep regular hours. Oh yeah, that's very hard. Especially being an EE student. Failed. Failed. Yeah. Because I'm lazy, homework and Netflix often gets in the way. And I'm lazy. You know what? I feel the same. I'm also extremely lazy. Lazy like a mushroom. How about that? Eating? Yes, not really. I would sometimes change for a couple weeks and fall back to the old habits. Yeah, I do that too. Yeah, not just you eating. Yeah, that's another. Yeah, oopsie. When I'm missing the old habits, I would start questioning whether the changes are necessary. Sometimes I make up my mind. Sometimes I just persuade myself that the old me is good enough. You know what? Eating, that is completely fine. I know, we would all like to be perfect. Well, I don't know. Okay, I have to admit that I'm a little bit of perfectionist myself. I can imagine that for many of you in NTU EE are probably also perfectionists. You would really like to be better. But you know what? Sometimes we need to really excuse ourselves. Allow us to be more flexible. And this is the time. that we all try to allow ourselves to be flexible. Just like NTU would try to allow us to be flexible. Just like Poly is trying to be flexible, right? With the assignments due days. And I will try to be flexible with the last exam. Yeah. Well, this is just the second week into this, self-motivated sort of social distancing. Okay. So it will get harder 2 weeks down the road. So I need to do something. And let's see. Jia Hong. Wait. Jia Hong. I thought you already submit. No? Is that Johnny? Oh, Johnny is team 4. I'm sorry. Okay. Jia Hong on behalf of team 5. Yes, that's great. Looking for changes and made the change. Sometimes it is frustrating. Wait, yes or yeah, yes. Sometimes it's frustrating that when you pay great efforts on something, however you see others working with you together, you will feel better because you are alone. I see. It feels a little bit better, right? If we are feeling bad together with you. Okay, so I'm feeling with you. Okay, they give you courage and maybe some change will happen soon. Yeah, I think that's if you are on a diet, looking to trim a couple pounds, it would be easier if you join like a yoga camp, right? Or exercise camp. Okay. Yeah, something like that. Oh wait, hey, who's replying you? Let's see. Okay, many are replying. Did you mean not alone? You feel better because you're alone? Okay. Yeah, so they're picking on you. You do have many friends, I can tell. Yeah. So like they like teasing you, Jia Hong. How did you get the goofy sign? Goofy emoji. Where is it? Oh, right there? Is that? Oh no, it's not quite. Where's the goofy emoji? I don't have it somehow. Okay. No, I give up. Okay, I'm goofy enough with this one here. Okay, Wei Yao. Yes, no. But sometimes the strong depression will give us the strength to change. Wow. Wei Yao. You are also a someone from the space somewhere. Yeah. You are a very strong person, I have to say. Very strong-minded. Good for you. But hey, you guys, if you see Wei Yao is a little bit down, make sure that you are there for him as well. Just like you are there for Jia Hong, or was it, I forgot, who else? Jia Hong. Angela here? Yes? No? Oh. In my case, it's about going to the gym and exercise and be healthier. Yeah, I do want that too. And my kind of exercise is swimming. But no, can't do that now. So then I turn to jogging. It's not easy because my laziness plus there's COVID now. Yeah. Oh, by the way, I need to tell you, the other day I went through Da'an Park. I saw people jogging with the masks on. They're so cool. I'm not sure if I will survive the jog with the masks on. Okay. Jean and Samuel, not really, because the motivation is always not strong enough. I see. It's hard. Okay, and Kevin for team 15. Yeah. And guys, by the way, so this is for today. So if you guys need to move to the next class, feel free to go. So I'm just gonna walk through the rest, just for my teams. Okay, Kevin, motivation becomes stronger, especially after seeing some incredible guys. Ooh, all right. Inspirations, isn't it? Failed. More cases. The environment pushed you to change. Otherwise, I would like to live like a lazy seal. You know what? My sister, the youngest one, said it once. She would really like to be a cat. And looking at Honey, my cat, there. That's a very good life. Don't you want to be just like don't you want to be a cat, right? A pet for someone. How we're here for Team 7. Yes, I've changed a lot and my life get worse already. Ouch. I started to use iOS instead of Android. Interesting. Yeah, definitely worthy an Apple. But where is the apple? Okay. So, hey, let me replace it with the mushroom. Sorry. Okay. It's not so easy since Siri often pops up suddenly and speak loudly. Yeah, I really didn't know how to close it at the first time. Yeah, of course. And 景祥 with 玉子. Yes, I want to start working out for almost a year. Yeah, almost. Finally, I registered about a month ago and then COVID-19. Sorry, gym is closed. Even though it's hard to make the change, life is still interesting. I like your answer a lot. It's complicated, isn't it? Complicated. Complicated in a way that it's also interesting. Yuan Xiang. Wait, Shi Wei already answered for you guys. Okay, I guess Yuan Xiang wants to say on behalf of himself. Yes, all the time. Yes, but in a wrong direction. Interesting. Yes, because as long as I relaxed, it will get worse. Poor you. Poor you. I can see that, there are lots of things that you want to do. Okay, I wish that you get everything that you want to do done, even though that you are also relaxed. But I'll have to say, human productivity gets worse when you are stressed. And sometimes relaxing oneself is necessary to be productive again. Well, that's why we have the summer break, which is coming up in just 3 weeks. Aren't you? Oh, wait, for you guys, it's 4 weeks. Sorry. Maybe a little bit longer in case you are taking courses with the final projects. But in the worst case, in 1 month, summer is right there. Even though we need to stay home or more or less around home, but it's still something worthwhile looking for, right? Yeah, maybe it's just that something there nice out there, worthwhile as pursuing, keep us going, okay? But guys, no matter how hard it is, I wish you are successful making changes, whatever it is. And that's the end of the session today. I'll see you again Thursday. Good. And we'll move on to the new topic, SDN. That's something that's very different from the traditional forwarding. It's the modern forwarding, flexible forwarding, general forwarding. Good. So, ciao guys.